Start.
Okay, good afternoon, everyone. My name is Tia Shemaya Wang, and this afternoon I'll be looking at land cover change across Barbados using remote sensing and GIS technology. I will first share the goals and objectives, then I will introduce the study area and the motivation behind the study. I will look at the methods and data used, and then we discuss the results before conclusion. The main goal of this study was to assess land cover change across Barbados between 2014 and 2021. And to do this, I used the Normalized Difference Vegetation Index to assess vegetation health and supervised classification method to determine land cover change between the 8-year time period. So Barbados is 166 square miles. It's located in the Caribbean and it's the easternmost of the Caribbean islands. Our highest point is Mount Hillaby, which is just over 1,000 feet. And from the latest population estimates for 2021, we have just under 270 persons on the island. 23% of the land is used for agriculture, and our main crop is sugarcane. Over the years, there's been an increase in commercial and residential construction, which has raised concerns about food security and the amount of arable land available to locally produce our own food, as we import about 70% of our food. The data used for this study was acquired from the US Geological Survey Earth Explorer portal, and I'm using Landsat 8 OLI surface reflectance. The reason I'm using this is previous studies done on the Caribbean, specifically on land cover change, have used Landsat products, so I'm using this as a comparison. The dates chosen for this study was strategically taken within the dry season, when humidity, rainfall, and subsequently cloud cover are climatologically at its lowest. So the first date chosen was in February 2014 and March 2021. The projection I'm using in the study is the UTM zone 20. So to compute NDVI, I used several geoprocessing tools to first scale my surface reflectance imagery. I'm using a scale of -1:1, so the imagery was scaled, and then I used the Landsat 8 equation to compute NDVI, which uses the band 5, the near infrared band, and band 4, which is the red band. For the supervised classification, I'm using a support vector machine classifier, and bands 1 through 7 were chosen to create composites, which were then used within the support vector machine classifier to help with our training samples. This was then clipped to the study area, and a number of spectral computations such as land and water, as well as vegetation analysis, was used to help acquire those training samples. 7 classes were chosen to train the supervisor, the classification, and the first one is the forest or dense vegetation, agriculture or crops, and these include various crops from sugarcane to corn, so they're all grouped into one category. The third group, bare soil or barren land, water or stream, and this includes small ponds, even ponds along golf courses, and grassy areas or inactive agriculture. The 6th class is urban areas, and because there is some cloud cover within the imagery, just less than 20%, this class was included to account for the cloud cover during the classification process. So an accuracy assessment is done after the classification using a number of geoprocessing tools. Again, firstly, the training samples were used to then extract validation sites, which were used along with ground truth data, which were then put in a confusion matrix to assess the accuracy, the overall accuracy of the classification. From the results for the NDVI, in the southern part of the island, you can see that there's been a decrease in healthy vegetation. Along the hillsides, these areas show roughly the same amount of vegetation health along the hillsides and also across the western parts of the island. To the north, looking specifically, these are areas where they're mostly crops and agriculture. And you can see that in 2021, there's been an increase in healthy vegetation in the north. Now, using the statistics from the histogram, which showed that the data was normally distributed, 3 classes were used to determine the loss and vegetation gain during the 8-year period. And from these statistics, 43% of the island had vegetation loss, with 57% experiencing no change in vegetation health. And there's just a very small area that showed vegetation growth. Island areas, just about 0.26%. Now, from our results, there are several reasons why we would have gotten the results we did. Firstly, the healthy vegetation in the southern part of the island. These may have been areas that are no longer in use or have been plowed, revealing bare soil. Along the hillsides, healthy vegetation is being maintained mainly because this area is remote and prone to land slippage. Therefore, urban construction would be limited. And the island is covered mostly by moderately healthy or diseased plants from the results. And this can be due to a wide range of crops at different stages of growth. Also, the time period I'm using is between 8 years, so the changes would be significantly small. From the classification, the accuracy assessment, it was showed that we had about 40 to 70% of the pixels being accurately classified for 2014. 96% of the forests were accurately identified, and this class had the highest number of pixels being accurately identified. The accuracy assessment showed a median level of accuracy of 67%. Similarly, for 2021, 47 to 80% of the pixels were accurately classified. Forests, again, had the highest level of pixels being accurately classified, and the level of accuracy was 58%, similar to that for 2014. Some of the reasons why we would have gotten the results we did, the resolution of the imagery used for the training samples was quite low, so that would have impacted the accuracy. Also, I'm using Landsat 8. The use of Sentinel-2 or satellite imagery with a higher spatial and spectral resolution would require a higher level of accuracy. Using more training pixels per class, I use 30 pixels per class, and including more classes instead of incorporating different crops into agriculture, separating these classes could have given a higher level of accuracy. From our results, looking in the southern section of the island again, it seems as though there's a decrease in agricultural lands. Also, it also shows an increase in grassland areas to the south. The northern part of the island, looking more closely, you can see that there's been an increase in grassland areas as well as agricultural areas in the northern part of the island. Along the hillsides, the forest areas seem to have remained unchanged. There's also some increase in forest areas across the western part of the island. Now, there's only one mangrove area in the island located to the southwest, as you can see from the bottom images. And looking to the bottom left, this area had bare soil adjacent to the swamp. And in 2021, you can see that there's an increase in grassland areas just adjacent to the swamp. A point to note, the blue areas in 2021 imagery, which shows that we had to change the water streams across the island. These are actually cloud shadows, which were cast in the imagery, and they had similar spectral signatures to those of. Now, after the classification was done, I looked at which classes changed to which, particularly classes that changed to agricultural areas, such as the grassy to agriculture areas shown by the red in the top image, and also areas that changed to urban, mostly grassy areas to urban areas, and agriculture to urban areas as well. Looking at the statistics, bare soil or barren land to urban accounted for the largest change with 23.2%. There was also a significant change from grasslands to agricultural areas, accounted for 18.7%. Grassy areas to urban areas had about a 10.4% change, and there were smaller changes for bare soil to agriculture. Looking more closely at the agricultural and urban growth across Barbados in terms of the total area that's changed, bare soil to barren land, bare soil or barren land to urban areas accounted for the largest change, over 300 square kilometers being changed to urban areas, and from grasslands to urban areas also had a significant change of over 250 square kilometers. You can see that there's been some increase in agricultural lands from our grassy areas to agriculture, and smaller changes from our forest to urban areas. So from our supervised classification methods, the areas where we see a conversion of agriculture to grasslands could be due to areas that were inactive or overrun by bush. Where we see a change from bare soil to urban areas could be due to an expansion of urban areas such as buildings and roads. And the change from bare soil to in 2014, these areas could have been cultivated during the 8-year time period. So in conclusion, there's been a decrease in healthier vegetation during the 8-year time period. About 56% of the land cover remained unchanged, and for vegetation gain only about 0.26%, and this is concentrated mainly in these highland areas. The largest change was from bare soil to barren land, which accounted for 3%, and there have been smaller changes from grassy areas to urban and croplands to urban areas. Some of the initiatives which have been implemented to promote vegetation growth on the island, both governmental and private, would have been tree planting initiatives. Some areas have been changed to protected lands. This is to limit urban development and also more efficient housing solutions. Thank you for your attention during my presentation.